Okay, so we have a small block of mass 0.5 kilogram. It's placed on a long slab of mass 3 kilogram as shown above. The slab at rest and the block the slab is at rest and the block has a speed of v naught of 4 meter per second to the right. The coefficient of kinetic friction between the block and the slab is 0.2. There is no friction between the slab and the horizontal surface on which it moves. On the dots below that represent the block and the slab, draw and label vectors to represent the forces acting on each block as the block slides on the slab. Okay, so for the block, we're going to have its weight pulling it down, so we'll have an MBG going down. We'll have a normal force going up, and that normal force is coming from the slab, so we'll make sure that we're specific there. So there's a normal force up, and we will put an S there so that we know it's coming from the slab. What else is acting on it? So this is after, so it's already moving at a speed of 4 meter per second, and this is after whatever put it at that speed. So the force that put it at that speed is no longer acting on it. So if that's the case, the only thing acting on it is friction. It's going to slow down. And so if it's moving to the right, friction must be to the left. Okay, and that's it for the block. For the slab, we're going to have mass of the slab pulling it down, or weight of the slab pulling it down. So ms times g. We're going to have a normal force that is coming from the ground, so we'll use a lowercase g to represent that. Okay, applying Newton's third law, we have this normal force from the slab on the block, so we should have an equal but opposite reaction on the slab. So there's a normal force from the block acting on the slab, and those two, according to Newton's third law, are equal. Okay, so same idea with friction. There's friction between the block and the slab that we labeled right here. There must be an equal and opposite force acting on the slab to the right. Okay, there is no friction between the slab and the surface that it's on, so there's nothing else. And that friction force is what accelerates the slab to the right. It's also what's slowing down the block. And that's it for those two objects. At some moment later, before the block reaches the right end of the slab, both the block and the slab attain identical speeds v final vf. So we want to calculate that speed. So there is actually a few ways that you could solve this. One of them we are going to do in this video. A second way to do it we haven't learned about yet, but it involves using momentum. So we might come back to this and solve it using a different method. Okay, so when you first look at this, it might not be 100% clear what to do. I know they're asking for a final speed between the block and the slab. I know that they reach that final speed at the same time. So most likely there's going to be some kinematic equations involved, but let's say you're not sure about that. I think a great place to always start is to apply Newton's second law. So let's do that for these objects. First of all, let's pick a direction to be positive, and let's make to the right is positive x. Okay, so let's do a free body diagram for the block. Apply Newton's second law for the block. So part B, again, you may not know where to start. This is a good place though. Let's just start with this. Okay, so second law for the block. So we're going to have F net in the x direction equals mass of the block times acceleration of the block. Okay. Since we said to the right is positive, that means that friction is negative, so we'll have a negative F equals mass of the block times acceleration of the block. They tell us the coefficient of kinetic friction between the block and the slab is 0.2, so mu k is 0.2. Okay, so we can replace F with a negative mu k times a normal force. Which normal force is that? It must be the one between the block and the slab. So this will be mu k times normal s equals mass of the block times acceleration of the block. Okay. So what you might notice by doing this is, okay, I've got acceleration, or at least I can find acceleration. So maybe at this point you might recognize I can find acceleration of each block and then apply some kinematic equations to figure out the final velocity. And that is what you do. So at this point, let's just solve for acceleration. So we're going to have acceleration of the block is a negative mu k normal divided by mass of the block. Okay, we need to get the normal force, so let's apply Newton's second law in the y direction, which is 0. Net force in the y direction, we have normal minus mg, so normal is equal to mg. Okay, so then acceleration of the block, if I plug that in for normal, will be negative mu k times mbg divided by mb. So acceleration of the block is just negative mu. These masses cancel out. So negative mu times g. Okay, so let's do the same for the slab. So we have F net in the x direction equals mass of the slab times acceleration of the slab. F net in the x direction, we just have friction equals m sub s times a sub s. Friction is equal to, well, we already found that. Friction is equal to mu k times the normal, and s equals msas, and the normal we said is mbg, so we have mu k mbg equals ms times as. Okay, and then solving for a, we're going to have mu k mbg divide ms. Okay, so at this point we have the acceleration of both objects, and so now we would use some kinematic equations. Okay, and so the kinematic equation I would use for this is v final equals v initial plus acceleration times time. Okay, and the reason why I'm using this is we know the initial velocities, we know the accelerations, and we know that they happen at the same time, so we can get rid of the things that we don't know. So for the block, the kinematic equation will be v final. The block has an initial speed of v naught, so v final equals v naught plus acceleration of the block times time. V final equals v naught plus, well, we said acceleration of the block is negative mu kg, so we can plug that in, so minus mu k gt. Okay, for the slab, we are going to have v final is the same. Initial velocity of the slab is 0 plus a of the slab times time, and a of the slab is mu k mbg divided by mass of the slab times t. Okay, so then what we could do is we have two equations and we have two unknowns, so we can get rid of, we can solve for time right here, and then once we have time here, we can plug that in to time right here, and then solve for v final. So time is equal to v final times, I'm going to multiply everything, multiply both sides by ms divided by mu k mvg. So we'll have time equals v final times ms divide mu k mbg. Okay, and then I can plug that in to this equation. So we have v final equals v naught minus, we have a mu k g times all of that stuff. So we have v final ms divide mu k mbg. Okay, and the mu k and the g cancel the mu k and the g right there. So we have v final equals v naught minus v final mass of the slab divided by mass of the block. All right, so then what we can do is get v final all by itself. So I'm going to add this v final ms over mv over. So we have v final plus v final mass of the slab divide mass of the mass of the block is equal to v naught. Factor out a v final. So v final times 1 plus m slab over m block equals v naught. And then divide both sides by 1 plus ms over mb. So we have v final is equal to v naught divided by 1 plus ms over mb. And then plugging in stuff that we have, v naught is equal to 4 meter per second. Divide 1 plus the mass of the slab is 3 kilogram, and mass of the block was 0.5 kilogram. That's equal to 4 divide 1 plus 3 divided by 0.5 is 6. So 4 over 7 meter per second. And if we get that as a decimal, let's see, 4 divide 7 is 0.57. So v final is 0.57 meter per second. Okay. Part C, we want to calculate the distance the slab has traveled at the moment it reaches v final. We want delta x basically. So looking at the picture, these things are going to move to the right and they're going to end over here, and they will have traveled some distance delta x, and we want to know what that is. Okay, so we can use a couple of kinematic equations. Let's use this one. V final squared equals V initial squared plus 2a delta x. Okay, so for the slab, V initial is 0. Acceleration is a of the slab, and we said earlier that a of the slab is equal to mu k mbg divide ms. Okay, and so we can use that for a and solve for delta x. So we have v final squared equals 2a times 2 times a sub s delta x, and then let's solve for delta x. So delta x is v final squared divide by 2a sub s, which is equal to v final squared divided by 2 times mu k G over MS. Okay, so if I plug that stuff in, V final squared we said was 0.57, or we could, if we want to get an exact answer, we could use, I guess, a more accurate answer, I should say, we could use 4 divided by 7. So we have 4 over 7 meter per second. We got to square that and then divide by 2 times mu k. Sorry for all the scrolling. Mu k is 0.2. 0.2. Mass of the block is 0.5 kilogram. G is 10. Divide by mass of the slab is 3 kilogram. I guess if we're going after accuracy, we should use 9.8 for acceleration. Okay, we'll plug that into calculator. So we're going to have 4 divided by 7, and we're going to square that, and then we have 2 times 0.2 times 0.5 times 9.8 divide 3, and we get 0.49979, so we'll say delta x is 0.5. 0.5 meters, I should say.